When the electron is confined to an atom, then the wavelength of the electron is on the order of the size of the atom here. And so it makes a difference, how many wavelengths can you fit? So this is similar to the scanning wave that we saw. The next allowed orbit for this electron would have another half wavelength in there, or the one below would be missing one half wavelength. And so if we were to change the orbit of this, although it doesn't orbit, we'd have to add another half wavelength or multiples of that half wavelength. And those would be allowed. Whereas a free electron, let's say in tungsten metal, what we see is that the wavelength is small compared to the size of the filament here. Here, lambda is relatively big compared to the size of the atom. And so lambda is the symbol for wavelength. Here. What would happen though is if we, and this is tungsten wire, what would happen is if we can confine the electron to a tungsten atom, then let's just take an atom here and blow it up here. So if we confine the electron to a tungsten atom, then all of a sudden, it had all this space, but now the electron is stuck in an atom. And so if you made a lamp using tungsten vapor, that is tungsten atoms, it would do the same thing. You get a line spectrum. That is, you wouldn't get a continuous rainbow, but you'd get only specific colors of light from there that are allowed for this. Does that make sense? And so the difference here is the wavelength here versus the wavelength when you're stuck in an atom makes a big difference here. And so now all of a sudden this wavelength is too big for its space. So this would be the analogy, a whale is stuck in an aquarium. A whale stuck in an aquarium is going to be highly confined, just like an electron stuck in an atom is highly confined in this way. But if the whale were out in the open ocean, then it could go any speed it wants. So here, it's easy to just add another half wavelength. Here, it'd make a fairly imperceptible change in energy. Here, another half wavelength would be a pretty significant jump in terms of the energy. And so this is what I meant by a free electron. A free electron isn't going to be confined to a small space or a small volume. And so what we call this is an electron in a box. Or an electron's a particle, so they call this the particle in a box. Okay, if the box is huge, then we can essentially think of this as a free electron. And so this would be an allowed energy. The next allowed energy is going to have one more half wavelength. And so the next higher energy has just one more half wavelength. So it almost looks the same. Let's say I had 1,000 half wavelengths in here. The next allowed one is going to be 1,001. Or let's say I had 1 billion. The next allowed energy would be 1,000,001. So if I had a billion and then 1,000,001, is there much difference in energy? No. Or the next lower energy would have 999,999,000 half wavelengths. This is allowed. And so what we see is that the energy, even though it's quantized, the energy difference here is negligible. And so it's pretty much a continuum of colors that are allowed. And so when we go from red all the way up to violet, we see the whole rainbow of colors from the tungsten wire once we excite it hot enough. Whereas in a tungsten atom, the next allowed energy is going to have, this is 3 half wavelengths, the next allowed energy will have 4 half wavelengths, which would be a more significant jump when it's confined to an atom because of that. And so we'd have to fit another half wavelength in here. There's only 3, now we're going to 4. Whereas if there were a billion half wavelengths here, and then we go to 1,000,000,001, then it'd be very little difference in energy. And so what we do is we see this in the energy level diagram. If you look at the energy level diagram for tungsten, there's going to be a jump. Okay, so let's go, with 2 half wavelengths, 3 half wavelengths. The next one is 4 half wavelengths. Next one's 5 half wavelengths, 6 half wavelengths, 7 half wavelengths. But when you get to higher numbers, like 1 billion half wavelengths, and 1,000,000,001, because there are an infinite number of allowed states, and eventually it's going to go to n equals infinity here. And so as the spacing gets closer and closer, then it's more of a continuum rather than discontinuous quantized spectra. But what we do is we see these transitions down here. This could be in the UV or the visible or whatever. And so we see these transitions. These transitions up here, or higher energies, could be in ultraviolet or X-ray. So when we have this, what we see is rather than a line like this one would result in a very specific wavelength here. This kind of area here results in what we call a band. Absorption or emission band. And here it is. It's fairly continuous. This band is going to occur at much higher energies, let's say, than this here. In the sun, you have free electrons, and so they're pretty much allowed any energy you want. It's just when the electron's confined to a small box, like the atom, we see this quantization. Does that answer the question, or someone? Okay, other questions? All right, today what I want to do is I want to do this experiment 8 here. I'm going to break experiment 8 into 2 parts. Part 1 is going to be Lewis structures, and then part 2 will be geometry. So let's take a look. And then I need to talk about experiment 10. Which is titrations. we're going to draw Lewis structures for both ionic compounds and molecular compounds. Ionic compounds, what happens with those is the elements on the right side of the periodic table want to gain some electrons. In ionic compounds, they can take them from elements on the left side of the periodic table. And then we'll form ionic compounds. But sometimes the atoms on the left side of the periodic table aren't so far left. If they're metals, no problem. On the left side, we have metals. But what if we have two nonmetals battling? Normally on the right side of the periodic table, we have the nonmetals. The nonmetals want to gain. If we have two nonmetals, then they're going to fight for the electrons. So if it's a metal and a nonmetal, no problem. We're going to get an ionic compound. But if it's two nonmetals, we're going to get what's called a covalent compound or molecular compound. And so molecular compounds are going to form when the atom isn't strong enough to completely take the electrons. They have to end up sharing the electrons. And sharing the electrons is what covalent bonds are all about. And so then number 2 is determine electron geometry and molecular geometry. That we're going to do later. Right now, we just want to be able to draw the Lewis structures. When we do this, this is the Lewis structures for molecular compounds. Now, this is not the Lewis structure for ionic compounds here, but the Lewis structure for molecular compounds, one, we want to show the linkage of the atoms within a covalent species. Yeah, so these are all going to be covalent bonds. We're all going to end up sharing electrons in order to get that octet. Not everything is going to want an octet. Like hydrogen and helium to fill the first shell needs just what we call a duet, 2 electrons to fill the first shell. But if it's the second or the third shell, we need 8 electrons to fill that. The S and the P orbitals. And so that's where we get the octet. And we're looking primarily at the first and the second shell. In the third shell, it's easy. The fourth shell gets a little bit more tricky because of the D electrons there. But we'll take a look at some of those as well. All right, these electrons may be shared in covalent bonds, single or multiple, or unshared, which are called lone pairs or non-bonding electrons. The following process is used to create the correct Lewis structures. So we have different processes. This set of processes here is great for more complicated Lewis structures. If we have very simple Lewis structures, then we can just visually see how they're going to share, like H2O, etc. We don't necessarily have to go through all these steps here for something like water. 1, count the total number of valence electrons. So the valence electrons are the outer shell electrons. They're going to have the highest N number. So when we look at the electron configuration, we can figure it out. Or we just look at the periodic table. The periodic table is going to basically tell us how many valence electrons there are, unless the atom has a charge. If the atom has a charge, then that's going to change the number of electrons, valence electrons. And sometimes the atoms will have a charge because sometimes we're dealing with anions or cations. And that's going to change the number. And so we count the number of valence electrons. For main group, they're just the group number. And so we use the Roman numeral group number. The number of valence for nonmetals is the group number minus 10. Depends if you use the Roman numeral or if you use the main, the 13, 14, etc. So this varies. It's pretty simple. It sounds more complicated. When the species is a polyatomic ion, the number of valence electrons must be adjusted. For anions, add electrons equal to negative charge. For cations, subtract electrons. Okay, number 2, choose the least electronegative atom as the central atom. The least electronegative atom is going to be at the bottom left. Arrange the other atoms around the central atom. So what we do is we have a center, and it's not always the case, but if we're going to have a center, we're going to get the atom that's the biggest atom, the least electronegative atom, the atom furthest down and to the left. The atom furthest down to the left is going to have the lowest ionization energy as well. There are some little hints. Hydrogen and oxyanions and oxyacids is usually bonded to an oxygen. So So hydrogen in acids, that is, acidic hydrogens, are bonded to the most electronegative element, which most electronegative element most of the time is going to be oxygen. Sometimes it's fluorine, but we'll bond it. Well, if it's oxyanion, then it'll be oxygen. Whereas non-acidic hydrogens don't need to be bonded to an oxygen. They could be bonded to carbon. They just won't be acidic. And that has to do with the bond polarity, which we'll talk about. Hydrogen-carbon bonds are non-polar covalent bonds. Carbon prefers to form 4 bonds. These 4 bonds could be, 4 single bonds, 1 double bond and 2 single bonds, 2 double bonds, 1 triple bond, and 1 single bond. So just any combination of that would be technically 4 bonds. In addition to carbon and hydrogen, other atoms have preferred number of bonds as listed below. These preferred numbers may have many exceptions and are used only as a guide when choices must be made. Halogens, typically 1 bond. Oxygen, typically 2 bonds. Nitrogen, 3 bonds. There are things that change this, though. Like, for example, if oxygen has a positive charge, then we can get 3 bonds. If nitrogen has a positive charge, we can get 4 bonds. If nitrogen has a negative charge, we get 2 bonds. And so there are adjustments that we make for these when it comes time to come up with the structure. When it can be avoided, like atoms usually do not bond with each other unless it's carbon. Carbon is the exception to this statement. It's commonly bonds. The primary thing is like oxygen. Oxygen doesn't like to bond to other oxygens. When you have oxygen single bonds, it creates what they're called peroxide bonds, and the peroxide bonds are inherently unstable. And so, whereas carbon-carbon bonds, single bonds, are stable. No problem with that. Place the valence electrons around the atom as follows. Okay, so we connect the atoms, and then we fill the octets to the peripheral atoms, and then we place any remaining atoms on the central atom. And if we don't have octets, then we add multiple bonds. And so we can follow these instructions here. When Lewis structure is charged, we place square brackets around it and then write a right-hand superscript indicating the charge. The correct Lewis structure, the atoms are correctly linked, all valence electrons have been used, atoms have an octet, a charge other than 0 is shown, except for hydrogen. Atoms have an octet. Species which do not have an octet, so these are some exceptions here. We'll talk about those a little bit more. So this is an example here. This is formic acid. Formic acid has this formula HCO2H. The first hydrogen is acidic. Whenever we have an acidic hydrogen, that's going to be bonded to the most electronegative element, which would be oxygen in this case. And so it looks like this hydrogen is bonded to the carbon, but it's not. This hydrogen is actually bonded to the oxygen here, and we always write the acidic hydrogen first. This second hydrogen is non-acidic here. Well, actually, it depends on how we write the formula. In this particular formula, the second hydrogen could be acidic. There are 2 ways of writing the formula for this class of compound. One way is like this, HCOOH. And then this would be what we call the acidic hydrogen. And so this would be formic acid. Acetic acid is this, CH3COOH. This would be the acidic hydrogen here. Now, these 2 are called condensed structural formulas. These are condensed from the Lewis structure. But we also have other formulas like this, HCH2O. That would be another way of writing formic acid. Another way of writing acetic acid is HC2H3O2. Okay, in this case, the acidic hydrogen is in the front. In both cases, the acidic hydrogen is bonded to the oxygen. It's not bonded to the carbon. And so these three hydrogens are bonded to the carbon here. This hydrogen is bonded to the oxygen here. There's some different ways of writing this. So we can see this hydrogen is what we call a non-acidic hydrogen. That's because the electronegativity difference between hydrogen and carbon is less than 0.5. Hydrogen is what, 2.2, depends on which table you use. Carbon's like a 2.5, 2.6. And so the difference is small. In Chem 1A, the numbers are slightly different. Hydrogen is 2.1, carbon's 2.5, about 0.4 difference. And so it's not very polar. The carbon's just slightly more electronegative than hydrogen, but there's going to be a good tug of war for the electrons here. When we look at this bond, there isn't a good tug. Oxygen is going to dominate this. And so oxygen pulls the electron cloud towards it. When it does that, it makes hydrogen deficient in negative charge density. When hydrogen becomes deficient in negative charge density, it makes this hydrogen more positive. The more positive the charge on the hydrogen, the more acidic it is. This hydrogen doesn't have much of a charge on it, so this is what we call a non-acidic one. This one has a charge on it because of the skewing of the electron cloud here. And so we call that a polar bond. A polar bond is going to have two poles to it. And so when we look at the oxygen-hydrogen bond, like this, there, and we look at the electron cloud, oxygen is quite a bit more electronegative, and so it pulls the electron cloud towards it. The electron cloud is negative charge density. So the result is a dipole. A dipole has two poles. There's going to be a negative pole and a positive pole. There are two ways to represent a dipole. One way of representing the dipole is by using this, delta. The delta symbol means just small, negative charge on the oxygen, and over here we'll have a small positive charge on the hydrogen. It's not a full negative charge. If this is a full negative charge, then we just write the -1 or just negative. And if this were a full positive charge, we just write plus there on the hydrogen. And so what we call these are partial charges. The partial charges, that's because the electron spends more time around oxygen than around hydrogen. We can't pinpoint where the electron is. This is a greater probability it's closer to oxygen, but sometimes it's close to hydrogen. The way we do is we time average this, and the time average comes out like this. Okay, the arrow always points to the negative end, and then we have a positive tail. The positive tail is over here. So the positive tail is on the hydrogen, and the negative arrow is on the oxygen. And so this is what we call a polar bond. This is a polar covalent bond. So give me a strong base. What would be a strong base? Hydroxide. And so hydroxide, this will be the Lewis structure for hydroxide. The Lewis structure for hydroxide has what we call 3 lone pairs here. And this is going to have a negative charge. And so the hydroxide, well, that negative charge is actually on the oxygen here. And we're going to look at how to calculate this. This thing that I've circled here is called a formal charge. And we need to learn how to do formal charges. So let me talk about formal charge right now. See if I have my periodic table. Okay, if we use the Roman numeral table with the A's, then here, Roman numeral 1A, that means one valence electron. Group 2A, 2 valence electrons. Group 3A, 3 valence electrons. 4A, 4 valence. 5 valence. 6 valence. So oxygen normally has 6 valence electrons. So when we look at this hydroxide, when we do formal charges, we split the bonding electrons evenly. So there are two electrons that make this line, the bond. And then we count how many electrons oxygen ends up with. So this is for formal charge. So how many electrons or how many dots does oxygen end up with here? Can you count them in the box? 7. And so there are a total of 7 circles here, 7 dots, 7 electrons. So we end up with 7 electrons. How many electrons does oxygen normally have? How many valence electrons does it normally have? 6. So it normally has 6. And so this is a normal valence electrons for oxygen. Has 6. In this structure, this is how many it has in this structure. So it has 7 electrons, it normally has 6. That means it came up with an extra electron. If it came up with an extra electron, it gets a -1 formal charge. And so this is what this comes in. What we do is this is -1 formal charge on the oxygen. How about hydrogen? Let's take a look at hydrogen next. How many electrons does hydrogen have in this structure? 1 electron. And how many valence electrons does it normally? 1 electron. And so 1 electron minus 1 electron gives us 0. So this is the valence, normal valence. And it has what it's supposed to have. So it's supposed to have 1 electron. It has 1 electron. Therefore, there's no charge. And so the formal charge on hydrogen is 0, but we don't write 0 here and circle it. Now this oxygen is different than this oxygen. If we look at this oxygen, what we do is we split the bonds in half. So there are 2 dots that represent the bond, 2 dots that represent this bond. So if we split the bonds in half, how many electrons does this oxygen end up with? 6. How many should it have? 6. So the formal charge is 0. It's broken even. In other words, it contributed 6 electrons to the structure. It ends up with 6 electrons. It has 0 formal charge, so there's no formal charge here. And so what's going to happen is this one's going to attack this hydrogen here. And so this is an acidic hydrogen. Let's go to a non-acidic hydrogen, which is going to be on this side. These 3 hydrogens in acetic acid are non-acidic, or that hydrogen over there is non-acidic. So we'll just look at acetic acid here. When we look at the electronegativity difference, carbon and hydrogen are comparable. Just carbon's is slightly more electronegative. Just slightly more. And so what this does is this creates, just the very, very slight polarization. Delta En is like 0.5 or 0.4. So this is kind of at the border. And so what we do is we have the very tiniest of delta pluses and the very tiniest of delta minuses. So tiny that we're going to ignore those. We ignore those, and then if hydroxide had a choice of hydrogens to attack, hydroxide's negative. So negative wants what? Negative wants positive. And so this hydroxide is going to see this this hydrogen, which is what we call polarized, and it has a partial positive charge. So this hydroxide, the oxygen here, wants that hydrogen. Whereas does this oxygen want these hydrogens? No, because these have close to zero charge. And so this hydroxide is not going to be very interested in these hydrogens because the charge is about zero. Does that make sense? And so this is why there are two different types of hydrogens here. We have the non-acidic hydrogens because the bond is pretty much non-polar. Just very, very slightly polar. And so this is a tiny delta plus and a tiny delta minus. Whereas this one is a much larger delta plus. This would be acidic. So in order to get an acidic hydrogen, you need an electronegative element to bond to it, like oxygen, like chlorine, like bromine, like iodine. Something that's quite electronegative. Things on the right side of the periodic table and up are more electronegative, like fluorine. But oddly enough, fluorine is not a strong acid. It should be a strong acid, but it's a weak acid. But there are other reasons for that. Okay, so what we'll do is we'll get some practice with this here. So this is a more complex structure here in formic acid. There are simpler structures that we can kind of figure out without having to do all these steps. So let's look at some of these simpler structures where we don't have to do so many steps. And that is very common elements would be like carbon. Carbon has how many valence electrons? Well, it's in group 4, so it's 4 valence electrons. And so this is going to want to form 4 bonds. These are what we call dangling bonds here. They want to form 4 bonds. Typically, we could have exceptions to that. And then we have nitrogen. Nitrogen, in order to complete its shell, we just need 3 bonds, or 3 electrons. Carbon wants 4 electrons, nitrogen wants 3 electrons. And so this is what we call lone pair here. And then we have these 3 dangling bonds in which we could form something. And so then we have oxygen. Oxygen only needs 2 electrons to complete its octet. And so what we do is we write 2 lone pairs and then 2 dangling bonds, like this. So it's going to form 2 bonds. That it could form, when I say 2 bonds, it could form 2 single bonds or it could form 1 double bond. Fluorine never forms more than 1 bond. And so that's the rule that didn't get placed here. Fluorine, only 1 bond. Chlorine, it can form more than 1 bond. And so only 1 bond for fluorine. How can chlorine form more than 1 bond? One, it's bigger. But 2, it has to do some other stuff. And so chlorine can form more than 1 bond. It's possible if we do something. If expanded octet or as you'll learn in Chem 1A, there's some ionic or ionic bonding occurs. When we have ionic bonds, then it's a positive and negative attraction. Chlorine, or chloride in this case, has how many bonds? Ionic bonds. We don't draw ionic bonds with a line here. This is just, these sticks are used to show connectivity, what the nearest neighbor is. But normally for ionic bonds, there's no line drawn. We draw lines for covalent bonds, but never for ionic bonds. So for ionic bonds, we just have a chloride like this. How many sodiums would be bonded to it? And so the chloride is the green. How many sodiums, gray, is bonded to one chloride? Well, it looks like 1, 2, 3, 4. But do you see there's a line going out this way? There's a gray or silver ball right there, but it's hidden. That's 5. And then do you see there's a line that comes out this way? That you can't really see unless we expand the structure. Turns out, a chloride that's stuck inside the middle of this lattice, in the middle of this crystal, is going to have 6 purples. 4 in the plane, 1 on the other side, and 1 on top. We're just looking at the edge. On the edge of crystals, we always have dangling bonds, because we got to stop it someplace. This thing can continue to extend out just by adding more ions. And so chloride bonds with 6 sodiums. Then 1 behind, you can't see. And so there's more than 1 bond to chlorine. Fluoride can do the same thing in the ionic, but as far as covalent goes, fluoride, only 1 covalent bond. As far as covalent bonds go, chlorine can bond to, like for example, in perchlorate, chlorine can bond to 4 oxygens. How it does this is it splits apart these lone pairs, makes them dangling bonds. But then what we run into is something called an expanded octet. That is, we have more electrons than this shell can accommodate. And so if we have more electrons in the outer shell of chlorine, then we have to fill that shell and go to the next higher energy shell. And so we'll talk a little bit about that here. But that can happen. And so let's take a look at perchlorate. So here are some examples of different structures. And you'll see that there's going to be different structures with different numbers of double bonds. Like this has 3 double bonds. What else do we have? We see different levels of structure. All right, so if we know the general bonding, so we got a neon. Neon has what we call an octet, and so its shell is filled. It doesn't want any more electrons. If neon got more electrons, then it would go into the next higher energy cell, which is going to cost a lot of energy, so it's unfavorable. And so we can kind of figure out what we're going to do here. Hydrogen has one dangling bond. And so if I have carbon here, how many hydrogens does it want? 4. So in this case, we don't need to do all these steps. I mean, the structure for methane is simple. Right? You just add a hydrogen to each of these dangling bonds here, and we'll complete the octet. The octet is going to be like this. So the carbon has 8 total electrons around it. Each hydrogen will have 2 electrons around it. 2 electrons we call a duet. 8 electrons we call an octet. Well, hydrogen only needs a duet to complete its shell. It's the first shell. Here, how many hydrogens will nitrogen want? 3, and then we form ammonia. You know, ammonia is a simple structure, so this one, I wouldn't even bother going through all these steps. Here, ammonia is simple. We can figure it out. We need 3 hydrogens to complete it. How many hydrogens does oxygen want? 2, and so that's simple too. Things can get more complicated. For example, carbon and nitrogen. You know, if we do that, or nitrogen and oxygen, if we do that, that gets more complicated, you know, depending on how we do it. We can do some simple ones. For example, carbon and oxygen can form carbon monoxide and carbon dioxide. Carbon dioxide is fairly simple here. If we do carbon with 2 double bonds, like this, and the oxygens will have 2 lone pairs, which we can draw like this, then that works. And so what we'll do is we'll have these 2 with 2 on one side, and those 2 with 2 on another side. And so we'd have CO2. Okay, let's take a look at the formal charges here. Do you see the formal charges? What we do for formal charge is we split the electrons, the bonding electrons, in half, and then the lone pair electrons belong solely to the oxygen. And so the oxygen is going to have 1, 2, 3, 4 that belong entirely to it, and then we're sharing. And so we're going to share 5, 6. And so altogether, how many electrons does oxygen have? 6. How much is it supposed to have? So it broke even. So we have 0 formal charge. This carbon, how many electrons does this carbon have? 4. How many is it supposed to have? 4, so it's even. 0 formal charge. This oxygen, same as this, 6 and 6. So that's 0 also. So there's no formal charges here. They're all 0. The formal charges, what we try to do is we try to minimize the formal charges. So sometimes you have multiple structures that you generate. If you have multiple structures that you generate, then choose the one with the lowest formal charges in terms of magnitude and number. And so this is good. Everybody broke even. However, how about carbon monoxide? If we look at carbon monoxide, let's see. Carbon wants 4, but nitrogen wants 3. So maybe not nitrogen, oxygen. Oxygen wants 2. But how do we do carbon monoxide? And so I got 4 dots, and so one thing is we could do it like this, maybe. We could have a double bond. And then carbon would be like that. But if we arrange the electrons like this, does carbon end up with an octet? Now, how many electrons does carbon end up with? 6. 6 only partially fills the shell. And so that's not going to work. And so it's not going to be a double bond. Oxygen has an octet. So if we take a look at the oxygen, oxygen's happy, but carbon's not. This oxygen is going to have a total of 2, 4, 6, 8 around it. So what we could try with carbon monoxide is we could try this. We could try a triple bond. That is, what we'll do is we'll take one of these electrons here, a lone pair from oxygen, and then put it into the bond here. So what that does is it leaves oxygen with one lone pair left. And then carbon has this. Now do we have an octet? Yeah, we're going to have an octet around carbon, and we're going to have an octet around oxygen. But how many bonds does oxygen like to form? Oxygen likes to form 2 bonds. Carbon likes to form 4 bonds. But in this case, oxygen formed 3 bonds, and carbon formed 3 bonds. And so it doesn't quite live up. And so this is what we call, these are the desired number of bonds if the atom is neutral. That is, if it has this 4 valence electron. Sometimes things don't quite work out. And so when we look at carbon monoxide, let's take a look at the formal charge. So what I'm going to do is I'm going to take this triple bond, split it in half, and then count how many electrons carbon ends up with. So how many carbon electrons are there? Valence electrons. 1, 2, 3, 4, 5. How many is it supposed to have? It's supposed to have 4. It ends up with 5, so it gets an extra negative charge due to an extra electron. And so this carbon, oddly enough, comes out negative. How many electrons does this oxygen end up with? 5, but it's supposed to have 6, so it's missing an electron. If it's missing an electron, it's going to end up with a positive charge. It's missing an electron. So if we have an extra electron, negative charge, missing electrons, positive charge. Now this is weird because what is the, if there's a tug of war for an extra electron, who should win, carbon or oxygen? Oxygen. And so what happens here is that oxygen should have ended up with the extra electron, not carbon. But if we gave the extra electron to oxygen, it screws up the structure because we can't generate an octet. And so in this structure, the octet overrides the electronegativities. And so octet is most important versus formal charge. And it gives carbon monoxide some interesting properties. And this is why carbon monoxide is very hazardous to your health. It's because this carbon has a negative formal charge. It makes it extra reactive. And so carbon monoxide is dangerous. Cyanide shows the same thing. In cyanide, we have an extra negative charge on the carbon, which makes it very reactive. So carbon monoxide and cyanide are very, very similar chemically. All right, this is just playing around with the electrons here. This one's pretty easy, or maybe those ones. These ones are especially easy. We don't have to go through the rule. The carbon monoxide is a bit more tricky. And so for carbon monoxide, let's go through the rules here. Or the steps. The first step is to sum the valence electrons. So carbon has 4 valence electrons. Oxygen has 6 valence electrons. And then the charge. There's 0 charge, so that means plus or minus 0. And so that gives us 10 electrons here. And then what we do is we do this. We draw a bond, a single bond between these here. Okay, then the next step is we complete the octet to the more electronegative element. The more electronegative element wants electrons more. So which one wants electrons more, carbon or oxygen? Oxygen. So what we're going to do is we're going to complete the octet around oxygen. That is by adding 6 more. So if we add 6 more electrons, 3 lone pairs and 1 bond, that gives us a total of 8 electrons around the oxygen. Then we count, how many electrons have we used? We've used 2, 4, 6, 8. How many electrons do I have? 10. So any leftover electrons goes on to the other atom, in this case, or the central atom they call it, but there's, these are only ends here. And so we end up with this structure here. And that gives us 10 electrons. And then we look for octet. Oxygen has an octet, but carbon does not. And so in order to make an octet, we start to share bonds. Here. And so what we're going to do is we're going to take a pair. We're not going to take this pair off carbon because that's not going to change anything. If I take this pair and bring it into the bond, it's called converting a lone pair into bonding pair, like this. It's not going to give us the correct number. And so we'll do this, and that's going to result in this structure here with a double bond. And now oxygen is only going to have 2 lone pairs. Oxygen still has an octet, 2, 4, 6, 8. Carbon, does it have an octet now? No, we got 2, 4, 6. And so I'm going to repeat this. I'm going to take another lone pair off oxygen and drop it into the bond here. If I take another lone pair off oxygen, I'm going to end up with a triple bond here. Okay, now does everything have an octet? Yeah. This carbon has 2, 4, 6, 8 total electrons surrounding it. This oxygen has 2, 4, 6, 8 total electrons surrounding it. So we have an octet. The most important thing is the octet rule. We need to get that satisfied. Okay, the final step here is to determine the formal charges. So carbon has normally 4 valence electrons, and in the structure it ends up with 5 electrons. And so that gives us a -1, an extra electron. And so it's 1, 2, and then half of these, 3, 4, 5. And then when we look at oxygen, oxygen normally has 6 electrons. In this structure it has 1, 2, 3, 4, 5 electrons. So 6 minus 5 is +1. It should have 6 electrons, it only has 5, so it has a deficit of 1 electron. And so carbon gets a negative formal charge, which we circle, and oxygen gets a positive formal charge, which we circle like this. And then we determine the formal charge. Now, if there are multiple structures, then we choose the one with the lowest formal charges. If we get formal charge to 0, is better than having these formal charges here. Sometimes we can't help it, we can't help but to have a formal charge. And so that's the case for something like ammonium. If we look at ammonium ion, let's go through the steps here. If we look at ammonium, nitrogen has how many valence electrons? 5. This is group 5. 4 hydrogens. Each hydrogen has 1 electron, so that's going to give us a total of 4 electrons. And then we have a +1 charge. A +1 charge means we have an extra electron or we're missing an electron. We're missing electrons, so we got to go -1 electron here. So 5 and 4 minus 1 gives us 8 electrons total. Now, normally we put the least electronegative element in the center. Hydrogen is less electronegative than nitrogen. But the problem with hydrogen is hydrogen can never be in the center because hydrogen only forms 1 bond. And so we can't put hydrogen. Hydrogen always has to be what we call a terminal atom. And so we'll have this. Okay, we've used up 6 electrons. And then what we do is we complete the octets to the peripheral atoms. Well, hydrogen doesn't want an octet. Hydrogen wants a duet because in the first shell, it only takes 2 electrons to fill it. And so hydrogen has a duet, duet, duet. Any remaining electrons, then we have this. We have 4 hydrogens, sorry, not 3 hydrogens. Any remaining electrons would go on whatever atoms need to, but are there any remaining atoms here? No. Does everything have an octet? Yes. Nitrogen has an octet, 2, 4, 6, 8 total around it. Hydrogen has a duet, so this looks good. So the octet rule, check. Okay, the final thing we do to this is we look at the formal charge. What's the formal charge on hydrogen? So if we split this bond in half, then hydrogen gets 1 electron, nitrogen gets the other electron. So if we split this bond in half, hydrogen has 1 electron. How many valence electrons does hydrogen normally have? 1, so it broke even. So 0, 0, 0, 0. However, nitrogen, how many electrons does nitrogen end up in this structure with? 4. How many normally? 5. So it's short 1 electron. If it's short 1 electron, is it positive or is it negative? It's positive, and it's 1 electron, so this gets a positive charge. And so we circle the formal charge like this. And then what we do is we add up all the formal charges. And so we combine all the formal charges, and then we get the net charge, which will be plus. So this is the formal charge. This is the net charge. The net charge is equal to the sum of all the formal charges. In this case, it's 0 plus 0 plus 0 plus 0 plus 1. Gives us plus 1. Okay, so we have a box for the Lewis structure for ammonia. You're going to do this. What you're going to do is you're going to draw the Lewis structure and we'll determine the formal charges. Then I'd like you to classify the bond. So is the bond in ammonia ionic, polar covalent, or non-polar covalent? And so you can do this on regular paper or in your notebook. You don't have to do it on the sheet here. We're going to change things a little bit. PCl4 plus, NOCl, NO2 minus, etc. So why don't you go ahead and start working on this, and then if you have questions, I'll help you out. So the formal charge on this nitrogen is 0. The formal charge on this nitrogen is that makes a huge difference in electronegativity. So this chart of electronegativities are for neutral atoms. And so that 3.0 is okay for this, but it's not okay for this. Because having this charge here is going to change the electronegativity of this nitrogen. And so when we do the bonds, just do it for a neutral species. If it has a charge, like in tetrachlorophosphonium, phosphorus is going to have a positive charge. That's going to screw up its electronegativity here. It's no longer going to be 2.2. Likewise, if it has a negative charge, it totally is a much lower electronegativity. If it has a positive charge, it's a higher electronegativity than this. If it's a negative charge, it's a lower electronegativity. So if the atoms have a charge, just skip it. So tetrachlorophosphonium, skip that. There's going to be some ionic contribution, but no.
Like for nitroso chloride, just 3.
No, 1 by 1. You just do them 1 by 1.
So what if they're different? Like let's say one's 0.9 and one's 0.4.
0.9 and 0.4, you just subtract it.
And then you subtract
the same one for the other. And so if you have different things bonded to it, let's say we had something like this. Then we look at this bond, nitrogen, hydrogen. Nitrogen, hydrogen here, nitrogen, oxygen here. This one's going to be reversed. This one is going to have a dipole like this. It's going to be polarized towards nitrogen, polarized towards nitrogen, polarized towards oxygen. And so these are, but I'm just asking you more simple. Are these ionic? No. Are these polar covalent? Yeah. So what I want to know is, what I want you to be able to recognize is non-polar covalent. Like, let me go back to this.
What's the difference between BG and L?
No, you don't worry about that. We're going to do that later. All right, is this bond polar or non-polar, covalent or ionic? This bond. This bond, well, hydrogen is 2.1, 2.2, carbon is 2.5. The difference is it's non-polar, it's less than 0.5 or less than 0.6. And so this is non-polar. This is polar covalent, this is polar covalent, this is polar covalent. And so basically just, okay, we have non-polar, polar, polar, polar.
You list all of them?
Hmm?
You list all of them? I figured you give it one name.
No, we don't give it. We do it individually, atom by atom. So we list all of them. So the way we would do this is like this. On the side, you'd write HC bond. HC bond, non-polar. And then the other bond, C double bond O, that's polar, covalent. C single bond O, that's polar. And then the OH bond, this is polar.
What if you have, it's one that's next to multiple, but they're all the same?
Then you just have to do one of them.
Just one.
Like ammonia, we have 3 of the exact same bond. All those are polar. The other thing you should do is this. To keep the structure from getting too messy, we'll do this on the side. And what you're going to do is you're going to put the dipole in here. So we're going to practice putting the dipole. The dipole is going to be this arrow that points to the more electronegative atom. Like that. Or you could write in the delta plus. This is going to be a delta plus, this is going to be a delta minus. Over here, this is delta minus, this is delta plus. Actually, maybe the delta plus, delta minus would be better. This is delta minus, this is delta plus.
Are we going to do that on a separate sheet?
Yeah, just do it on separate. Don't do this either in your notebook or on notebook paper. Don't do this in the report sheet of the manual.